This is not right. Oh. Hey, guys, are you there? Sorry. I tried to start this meeting and it said I had another meeting going and I'm not sure what I did wrong. All right. You guys hear me okay?
Yeah.
Okay, thanks. All right, you'd think 3 weeks into this I would have learned how to use Zoom properly, but it still messes me up sometimes. So I'm doing my best, bear with me. Look, I got additional lighting. I don't know if it shows better for you guys. So when you'll see when I turn onto the paper, you should be able to see the paper a little better now too. All right, so how's everybody doing? Anything that you need to tell me? Anything you need to ask me? All right.
I heard that an important mathematician has passed away this week called John Conway.
John Conway, yes, a very sad loss. In fact, he died from this new COVID infection. He was about 82 years old. Of course, mathematicians, anybody in their business, you hate it when a distinguished member of your community passes away. But I got to tell you, Conway was an especially unusual person. He was just quite a personality, I guess. I mean, he proved important theorems and made some discoveries, but he also he had a very kind of like a playful spirit. So he was the person who would demonstrate his theorems by juggling something or something like that. He was always coming up with very...
I heard how much he was interested in games and so on.
Yes. Well, he was interested in games, like games that you play. He was also interested in a branch of math that's called game theory, which is not really about games, but except in a very abstract sense. There is something that's very familiar to computer scientists called the game of life, and it was an early example of something that now it's called a cellular automaton, and that means that you imagine a picture that's just made of a bunch of cells that are darkened in as 0 and 1 or something like that. And then there are some rules that says, okay, when I'm going to turn the crank, and when we turn the crank, we'll move from this state to another state according to some predefined rules. And if I recall correctly, he set it up so that you would look at cells in a little, Cartesian grid, and some of them would be...
Depending on the number of neighbors, some cells would live or die, kind of like that, right?
Correct, yeah. So when you say live or die, now see, this is why it's the game of life, and that's Conway's attitude coming in. He's making it very, he's trying to make it very kind of human, describing cells as alive or dead. And most mathematicians would say they're either black or white, or they're 0 or 1, or something like that. But then the state of a cell in the next moment depends on counting how many of its neighbors were alive in the previous moment. And it's just some rule, and you write it down, and then you say, okay, what happens? So what happens if you start with the entire screen black? Well, then it stays black forever. Or what happens if you start with the entire screen black except for one cell that's white? Or what if 2 or 3 or a square or whatever? And you discover that certain kinds of patterns emerge. And in particular, they can be the darndest little things. You could write up you can show a little shape that's called a glider, and you discover that according to the rules that pertain to this particular cellular automaton, what you'll see is that in each successive stage, you get exactly the same shape, except it moves and it kind of glides across the screen. And so, I mean, it becomes something that you can play with, but from the perspective of theoretical computer science, this is important because a few of those kind of basic constructions demonstrate that you can actually do all certain, what's called the Turing complete type of calculation. I forget the details exactly, but embedded within this really simple so-called game of life, you could, in principle, carry out any calculation that's done with a kind of a classical computer. So that's just part of Conway just playing with games, and it turned out to have a lot of applications to, well, like I say, theoretical computer science and stuff. I will also tell you where I first heard them was when you take your abstract algebra course, at some point you discover groups. We've mentioned them a little bit in our class. There are sets in which you have a binary operation that's associative and an identity element, and every element has an inverse. And that's it. Those are the only rules, the only definition for a group. It turns out that describing all groups is kind of like trying to describe all chemical compounds. It's just a fantastic array of different possibilities, although on some level, every chemical compound is just a mixture of its elements. And there's only, well, now there's about 100 and some odd elements that are known. And in the same way, every finite group can, in some sense, be decomposed into a few types of finite groups that are called simple. And there's a few relatively easily understood categories of these things called the simple groups, simple finite groups. But then it turned out that people discovered that in addition to a few families, there's some exceptional ones. It turns out there's exactly 26 exceptional ones, and one or two of them were discovered by Conway. And he just came up with these very intricate kind of combinatorial designs. And when you look at the symmetries of these things, it turns out that those describe the groups that are now known by his name. So a fantastic figure in mathematics. He's been at Princeton for the last few decades. I forget where he was after that. That's quite tragic. He was 82. I mean, I guess at some point, everybody dies sometime. So. Yes, here somebody posted a link to the chat. Yeah, so yeah, you can play with the game of life. It's a lot of fun. I don't know actually anything that Conway did in number theory, I'm sorry to say. Maybe something, but I don't remember.
On Wikipedia, I saw that while he was a graduate student, he proved one part of a conjecture from an English mathematician, I don't remember, about this writing integers as sums of cubes or squares, like Lagrange's theorem.
I did not know that.
It was a minor proof, I guess. I don't know.
Huh. Interesting. Okay, so yes, I'll just mention that we've been talking about number theory in a lot of ways. We've been spending a lot of time on modular arithmetic, but throughout the course we've been focusing on stuff related to primes. There are other questions in number theories that you can ask that don't really depend so much on prime factorization, and one of them has to do with questions like, what are the numbers that you can write as a sum of 2 squares, or 3 squares, perfect squares, or 4, or 5, or however many, or same thing for cubes. And there's a whole family of questions that you could ask in there, really just idle curiosity kinds of questions, or at least they sound that way until somebody actually proves a theorem and you think, wow, that sounds impressive. So I was hoping actually to do this in the last few weeks of the semester. One of them, for example, is Lagrange's theorem that says every single positive integer can be expressed as a sum of 4 perfect squares. So that's kind of clever. And I don't remember what Conway's contribution was, but yeah, now that you mentioned it, there was I remember he did something like that. I can't remember for sure. Anyway, maybe we should get back to our stuff. So we were talking last time about some of these multiplicative functions, and one of the results that I mentioned had something to do with the sum of the divisors. Namely, there's this classification of some numbers as being perfect, and in the closing minutes, somebody asked me about, are there infinitely many perfect numbers? Perfectly fine. That's a natural, good question. And I have a partial answer for that. So let me show you what I do know about this. It's not what I know personally, but this is mostly due to Euler here. So here's some theorems about perfect numbers. Oops, how do I? There we go. So remember, so n is a perfect number. What that means is that, well, in symbols, it says sigma of n is equal to 2n. And recall, this means the sum of all the divisors. So the more old-fashioned way of saying it is that the sum of all proper divisors of n is equal to n. Proper divisors means a number that's smaller than n, a positive integer that's smaller than n, but it divides n. All right, and our easiest examples are n equals 6, so the divisors are 1, 2, and 3. The proper divisors are 1, 2, and 3. And then I mentioned 28, which was the divisors are 1, 2, oh, not 3, sorry. 1, 2, 4, 7, 14, and then 28 is 28. What you may notice in both of these cases is that the prime factorization is kind of interesting in these two cases. We have established that the sigma function is multiplicative, so if you ever needed to evaluate sigma of n for any integer n, one way to begin would be to factor n into its prime powers. So let's just try to check this result by factoring these numbers. This is 2 times 3, and this is 2 squared times 7. And when you go to compute the sum of the divisors, well, sigma of 2 times 3 will be sigma of 2. That's the sum of all the divisors of 2. That's obviously just, oops, sorry, 1 plus 2. And then since 3 is prime, sigma of 3 is 1 plus that prime number, which is exactly a power of 2. It's 4, which is exactly twice that power of 2. And in the same way, the other one, oops, 7, you would take sigma of 2 squared, so now you're adding the powers of 2 up through and including 2 squared times, well, 7 is just a prime to the first power, so that's 1 plus 7. That part gives you a power of 2, and which is 1 more than the power of 2 that we started with. And this is exactly the prime that we had before. So in other words, the pattern seems to be that you have a power of 2 and a prime, and when you take sigma of this, the prime turns into a power of 2. In fact, it ends up being the very next power of 2. And the sigma of this power of 2 then turns into the prime, except it is easy to add the powers of 2. I don't know if you have followed this through in general, but when you add a bunch of powers of 2, all the powers of 2 up through and including one of them, what you get is a number that's 1 less than the very next power of 2. So these two things kind of tie in together, and they give us the following theorem. If the number 2 to the nth power minus 1, call that p, is prime, then the following number is perfect. You take 2 to the 1 less power of n times p, and there's going to be a perfect number. And the proof, so that follows the pattern that you see in these first two. Here's 2 to the second power minus 1. And if I drop 1 from that exponent, I get 2 to the first power, which is what you see here. This one is 2 to the third power minus 1. Drop down 1 exponent, and you get just 2 squared. So that's actually what you're going to see in general. The proof is very similar to the computations that I was just doing. Sigma of capital N is, well, let's see, this capital N is, there's a power of 1 prime, here's a power of another prime, and since sigma is multiplicative, I can write this as sigma of this power of 2 times sigma of p is, the only divisors of p are 1 and p. And these two parts can be rewritten a little bit. I'm assuming in the first place that p is 1 less than a power of 2. So when you add 1 to it, you just get that power of 2. But this, on the other hand, this is a little piece of, I don't know, combinatorics or something. You prove by induction on n that when you add all the powers of 2 up to, but not including 2 to the nth power, the sum will be 2 to the nth power minus 1. This is obviously true when n is equal to 1, for example, because you only have a 1 here and a 1 here. And if it's true for some value of n, then if you write down the corresponding equality for the next value of n, all you will have done is added 2 to the nth power to the left. And when you add 2 to the nth power over here, 2 to the n plus 2 to the n will be twice 2 to the n, which is 2 to the n plus 1. So that's the proof of the inductive step to show that those two things are actually equal. Or it's a geometric series, and you have a formula for a geometric series. The denominator is 2 minus 1. Anyway, from the formulas we started with, this is the p, and this is 2 times 2 to the n minus 1. So here, except for the 2 there, the rest of this is exactly the n that I started with, and I did, in fact, get 2 times capital N. So such a number, capital N, is perfect. Now this takes us down a little side road of saying, oh, that's interesting. So are these things prime? I mean, I took the case when n was a 2. Well, let's see, when n is 1, this gives you the number 1, which is not prime by definition. When n is 2, you get a 3. When n is 3, you get a 7, and both of those things are prime. Of course, when you look at the next case, 2 to the 4th minus 1, that one's not prime. 16 minus 1 is 15, and of course that factors. You should have expected that this one was not going to be prime, because we've actually talked about how to factor expressions, factor integers that are written as special cases of polynomial expressions. This number isn't prime, but then again, almost no number of the form x to the 4th minus 1 can ever be prime, because you can factor this number. For starters, it's x squared minus 1 times x squared plus 1. And that's exactly the situation we ran into right here. When this is 4 squared minus 1, and it's 2 to the 4th means 4 squared minus 1, so that'll be the 4 minus 1, which is here, and the 4 plus 1, which is there. So when you have, when you're looking for primes among the Mersennes, you shouldn't ever use an exponent of 4. For that matter, you almost never should use an exponent of 2, because that part can be factored, although we already did have an example of a prime of this sort, namely the number 3. That was 2 squared minus 1, and that came out to be prime. But the reason that worked was because this factor, x minus 1, yeah, it's a factor all right, but when x is equal to 2, that factor becomes a 1, and that doesn't destroy the possibility that this thing would be prime. So that does cause us to go back here and say, oh, we should make sure when we say that this quantity can never be prime, we better make sure that neither of these factors is either a plus 1 or a minus 1. But of course, x squared plus 1 is positive. That can never be equal to a minus 1. And it can't be equal to a plus 1 either, unless, of course, x is equal to 0. If x is equal to 0, though, this doesn't come out to be, I mean, the number negative 1 is not considered prime. And this other one over here, this could be a negative 1 if x is 0, again. But it can never be a plus 1, because if x squared minus 1 is plus 1, then x would have to be a square root of 2, which is not an integer. So anything of this form is never prime. In fact, anything of this form is never prime unless x is equal to 2. And when I say never, I mean as you consider all integer values for x. As a special case, then, you can apply this not just to cases when x is equal to 2, but you can also think about when x is a power of 2. So if you considered a Mersenne number, oh, I'm sorry, I've started to use the word Mersenne. Mersenne is somebody's name. These things are known as Mersenne numbers. And when you consider any power of 2 for your x, then squaring such a quantity would give you the number 2 raised to an even exponent, and that would give you a factorization immediately, which demonstrates that this number can't be a prime unless one of these two factors is either a plus 1 or a minus 1. And we really just considered all of the possibilities. The only one that would ever give you a prime is in the special case when n is a 1, so 2 to the 1st minus 1 is a 1. So this is never prime unless n is equal to 1. In fact, this line of reasoning leads us at some point to discover this theorem. If n is, if 2 to the n minus 1 is prime, then n is prime. So I've already set up here that the exponent can't be even, except in the case when n is 1, because 2 times 1, that is still a prime. That actually is consistent with this. But all the other even numbers are out. Well, it turns out not just the even numbers, but the multiples of 3 are all out as well, and the multiples of 5, and so on. And the proof is actually along the same lines as the proof that I've given up here. Because if n is if n is not a prime number, so I'm going to prove the contrapositive of this. Rather than showing if this is, I'm not going to assume that this is prime and then prove something. Instead, I'm going to assume that n is not prime and show you that 2 to the n minus 1 is also not prime. So let's have it. If n is not a prime number, that means that you can write n as a product of two numbers that are greater than 1. And what I want to do with that is to use the factorization of the polynomial x to the n in the same sense that I did those two. I don't have to find the complete factorization. I mean, I could have factored this one further, but I don't really need it. But I do want to at least get some part of a factorization. If you look at x to the n minus 1, that will mean it's x to the a to the b power minus 1. And then thinking about this as this part as, let's call it y to the b power minus 1, that's now a polynomial in y, which I can find at least one factor of. If you think about the roots of this polynomial, one of them is certainly y equals 1. So we have y minus 1 as a factor. And I can actually literally do long division to divide this into that. You would discover the other polynomial is y to the b minus 1 plus y to the b minus 2 plus and so on. Now I said you could check it by doing long division, or you might actually recognize the formula for the sum of a geometric series. The sum of those terms, those powers of y would be this power of y divided by that. I mean, this expression divided by that. So now substituting back in what y is, this would be written in the form of x to the a minus 1 times all the rest of that stuff. And that appears to give me a factorization of my initial number, x to the n minus 1. For any integer x, I've got an integer here on the left-hand side, and on the right-hand side, I now have a factorization, at least a partial factorization of the number that's on the left. As before, as with the other examples that I did with you, though, I should check to make sure that this factorization, that this integer is neither a plus 1 nor a minus 1, and the same thing over here. So let's do that. If I thought that x to the a minus 1 were equal to negative 1, of course, that would imply that x is equal to 0. And then you would just have the number negative 1, which isn't a prime. If x to the a minus 1 is equal to plus 1, that's a little harder. That implies that x to the a power is equal to 2. So how can you write 2 as a power of an integer? Well, there is exactly one way to do that for integers x. The only way to do that is to have a equal to 1, and of course x equal to 2. And that's forbidden when I set up here that I had a factorization with the number a being greater than 1. So it's not this factor that's ever equal to 1 or minus 1.
Excuse me? Do you mean at the very top, like if x to the power of a minus 1 is equal to negative 1, that a is equal to 0? Instead of x is equal to 0?
Yeah, what about that?
Supposed to be a is equal to 0? Or does
no, actually I meant, well, I should have said x to the a is equal to 0. If I add 1 to both sides, then it just says x to the a is equal to 0. So some power of this integer x is equal to 0, but no power of an integer is ever a 0. No power of any real number is equal to 0 unless the base is 0, right? if you multiply any non-zero real number times itself over and over, you never get 0. That's, well, yeah, it's a feature of the real numbers, or in fact, any integral domain. You can never have a product equal 0 unless one of the factors is 0. So it's x that would have to be equal to 0 at some point. And I mean, there's, you know, as I'm doing this, trying to factor integers that you get as a power of an integer minus 1, you could, for example, have plugged in x equals 0, and then you might say, well, at least if I plug in x equals 0, I'll get a prime. I mean, that would be the one case that appears to give a factorization, and then I would say, no, it's not really a factorization because one of these factors is a unit. Remember units? But unfortunately, when you plug in x equals 0, then the number you're looking at is a -1 on the left. So that's not a prime either. I mean, ultimately, I'm going to be plugging in powers of 2, of course. So it's not really interested in x equals 0 anyway. Now, you could worry about, hey, maybe this other factor is a +1 or a -1, but I guess I could be worrying about the possibility that y is a negative number, and then these powers could be alternating in sign, and potentially I could get a lot of cancellation. But let me just cut to the chase here. If I start off with a positive integer for x, then y would be a power of that, and therefore it's also a positive integer. And if you take powers of a positive integer and add them up, that's certainly going to be positive. So you're going to, when you finally add in the +1, you'll end up with something that is itself greater than 1. So let me just say, I'm now restricting my attention to x's that are positive. This other factor, y to the b minus 1 plus y to the b minus 2, etc., that's not equal to -1, of course, because it's greater than 0 in the first place. And it's not equal to +1 either, because all those other terms are non-zero. The only exception would be, I do have to be careful in here, that's true unless either y is equal to 0. And that would happen, again, only if you, well, I said positive integer, didn't I? Well, positive, greater than or equal to. But unless x were equal to 0, you won't get y equal to 0. And if x is equal to 0, you'd be stuck with a -1 on the left. Or there is another possibility. This expression should be interpreted as saying you begin with the number 1, and then you keep adding in powers of y, stopping just before you add in y to the bth power. Well, you know, if b were equal to 1, that would mean you would start with the summand of a 1, and then you don't add in anything else, in which case you would get exactly a 1. So there are just these two cases that do allow you to get this long expression equal to +1. Either you have a y equal to 0, or b is equal to 1. So in the special case where b is equal to 1, then this would just be a 1, and what looks like a factorization would not be a factorization of this integer. But I'm assuming that b also is greater than 1. So I had to use the fact that both a and b were proper divisors of n. In other words, I had to know the fact that n really was not a prime number. So in the old grade school sense, you really could factor it into two other integers that are both bigger than 1. And in that case, the fact that a is less than 1 prohibits this factor from being a +1. And the fact that b is greater than 1 prohibits this factor from being a 1. So now you've got your positive integer written as the product of two other positive integers that are not units, which means that this number would be composite. So the conclusion is that x to the n minus 1 is composite. And I didn't actually need to know that the x in question is 2. It's actually a composite for all x, all positive x. So I got a little bit more than I bargained for in this theorem here. Now, by the way, the case of x equals 2 is really the only case that's really of interest, because if you think, hey, He's about to tell us all about the primes of this form. I think I'll go off on the side and worry about primes of some other form, like maybe what about looking for primes of this form? I don't know. Anybody want to look for prime numbers of this form? Don't spend too much time looking for primes of that form, because 3 is odd, so all the powers of 3 are odd, and when you subtract 1, you're going to get an even number. And there's not too many even primes except for 2, and that is of this form when n is equal to 1, but no other case. So looking for primes that are 1 less than a power of an integer, well, really the only case that's really of interest is the case where the base is 2. All right, actually, just as a little side note, I'll just say, I'll invite you to look up the following thing online, the Cunningham project. There were quite a few people looking at these Mersenne numbers and things related to this, and of course they knew that this wasn't prime, but you might say, well, yes, I see that it has to have a factor of 2, but once you throw away the factors that you kind of automatically know about, the factors that come from this kind of factorization, maybe the rest of it is prime. And so people asked for, could you just please calculate for me the prime factorization, the factorization into primes of numbers of this form at I don't want to use the letter A, x, well, just say x to the n minus 1 or x to the n plus 1 while you're at it. Try both of them for small values of x and n. And this is not so much a mathematical bit of research, because after all, they're just integers and we know that they all have prime factorizations. But it did become a test of computer science ability. People wanted to know what's the best way to actually find factors of some big numbers. Obviously, powers of an integer will start to grow very fast. And so for some decades, this was, and maybe it's still going on, I'm not even sure, people would just collect tables of all the factorizations of numbers that are 1 more or 1 less than a power of 2 or a power of 3 or a power of 10, for instance. Okay, so to return to our Mersenne numbers, looking for primes among them, which is going to be useful for finding perfect numbers. If you want to find a prime among them, you better restrict to an exponent, which is itself a prime. Well, okay, so let's do that. Let's go run through some prime exponents. You could look at 2 to the second minus 1, that's 3, that's a prime. 2 cubed minus 1 is 7, that's a prime. How about 2 to the fifth minus 1? Well, that's 31, that's a prime as well. And so, according to this theorem here, since the number 31 is a prime that's 1 less than a power of 2, I should be able to get a perfect number by multiplying 31 by the next power of 2 down from here. In other words, if I look at 2 to the fourth minus 31, that's 16 times 31, and that comes out to 496, and there's your next perfect number. Well, and what's next? 2 to the seventh minus 1, that turns out to be 32, 64, 128, 127, and that is prime as well. And I'll let you multiply. It would have to be 127 times 2 to the sixth power, that's 64. So you end up with a number that's in the thousands, and that's your next perfect number. By the way, you might have noticed the pattern. There was one perfect number of 1 digit, and then another perfect number of 2 digits, and now this perfect number, I think it's, I don't remember, actually, I don't remember the digits, but it's 4 digits long. And so people had this idea that, hey, maybe you're going to get 1 for basically every power of 10. But unfortunately, the next thing to check in this list would be 2 to the 11th minus 1, which is precisely the number that I asked you guys to think about in the homework. And the number 2047 turns out not to be prime. Although the exponent of 11 is prime, This thing factors, in fact, it factors as 23 times 89. So that tells you that you, where'd it go? In this theorem, the converse of this theorem is not true. You can have prime exponents without the 2 to the n minus 1 part being prime itself. So unfortunately, we don't get another prime number that's about this big. The next one I believe is prime, but I don't want to go there. So it's 248, 4,096, 8,192. So there, this one, I believe this is prime. I don't recall for sure. Don't quote me on that. Anyway, this is an interesting family of numbers for which you can see there seems to be a high proportion of them that turn out to be prime, and the ones that do give you a prime number turn out to be of some other interest. They do give you these perfect numbers. So people have looked for prime numbers of this type. If, for example, you could find an infinite collection of prime numbers of this type, then that would give you an infinite number of perfect numbers. Oh, so yes, 8,128, somebody did it for me. Thank you, Thomas. I kind of remembered those digits, I just wasn't certain of them. So unfortunately, so let me give you this question. Are there infinitely many Mersenne primes? And the answer is, we don't know. So nobody has a good way of proving that that all of the Mersenne numbers past a certain point turn out to be composite. It's possible that such a thing would exist. You could imagine that somebody would say, oh, well, for all sufficiently large exponents, in the case where the exponent is, one more than a multiple of 4, then you have this factorization, and if n is 1 less than a multiple of 4, you do that factorization. Nobody has found such a kind of a theorem. In fact, the expectation, I guess, is that there are infinitely many primes in this family, just because we seem to keep finding them. People keep grinding these things out on the computer, and they check that more and more of them are prime. But it's really, really hard to prove a theorem that says all the numbers that you get in the following way are prime. There's really basically no good theorems like that. So in particular, there's really no good theorems that say that we can prove there's infinitely many Mersenne primes just from this subfamily or that subfamily. So that's an open question for you. If you want to get rich and famous in the world of mathematics, answer this question one way or another, and people will beat a path to your door pretty darn fast. I would like to tell you a couple of other things in this line of thinking, though, because they get to use some of the other facts that we have discussed. Now I want to point to the two factors that we found for this particular Mersenne number, 2 to the 11th minus 1. I discussed this with some of you guys in office hours. You may have noticed that when you take these two primes, they have something in common. Both of them are 1 more than a multiple of 11. In fact, they're 1 more than a multiple of 22. That is, in fact, a theorem. Suppose that you start off with an exponent on the Mersenne number, which is prime, and you have a divisor q. It's a prime, I'll say in parentheses prime, and then I'll remove this later. But if I have a prime divisor of this Mersenne number, 2 to the n minus 1, that'll be capital N. Then in fact, this number q is congruent to 1 modulo that prime exponent. And in fact, I'll go a little bit further. It's congruent to 1 modulo 2n. So q has got to be 1 more than a multiple of 2n. In this case, any divisor of 2 to the 11th minus 1 has to be 1 more than a multiple of 22. So when you're looking for prime divisors here, the very first one you would check would be 23. And of course, you could just divide the 23 into that to get the other one. But the other things that you would check would be 23. The next number in this list would be 45, which isn't even prime, so I don't need to bother with that. And the next after that would be 67, which does not divide this. And the next one after that is the 89. So you would have found all the prime divisors of 2 to the 11th minus 1 quite quickly if you'd used this theorem. Well, I wouldn't give you a theorem if I didn't have a proof. So let's have a proof of this one. So here's my thinking. If you tell me that Q is a divisor of n, then that says that, is a divisor of this number, capital N. That means that 2 to the little n minus 1 is congruent to 0 modulo little q. Or in other words, 2 to the n is congruent to 1 modulo q. Well, okay, that's cool, but just forgetting about the Mersenne numbers and thinking about n as being anything interesting, if you just use the fact that q itself is a prime number, then, well, we've already discussed the issue of what powers of what kinds of things will give you something that's congruent to 1 modulo q. That's the Fermat theorem. So what you know from the Fermat theorem is that 2 to the qth power, 2 to the q minus 1 power is also congruent to 1 modulo q. So now you've got two separate exponents on hang on a second. You have two separate exponents on the 2 that'll both give you a 1 modulo q. Hang on, something's bothering me here. Something is wrong. I didn't want. 2a has to divide. I'm getting a little nervous. I think I'm getting lost in my proof. Let me show you what I was going to do next. Okay, for my next trick, what I would like to do is I'd say, oh, I've got two different powers of 2 that are both congruent to 1 modulo q. What I would like to do under those circumstances is think about other exponents that I could put on the 2. In fact, I'd like to find the smallest exponent that I could put on the 2 to get 2 to the what being congruent to 1 modulo q. I do that in part because the very next thing that I want to discuss with you guys is this general idea of looking for what is the minimal exponent that you can put on an integer to get that power to come congruent to 1 modulo q or something else. So today is maybe the first day that I'm doing that. But I have a recipe to give me the smallest exponent that I can conclude I can put on the 2 just from these two pieces of information. Namely, if you look at all of the numbers that are a multiple of n plus a multiple of q minus 1, if you raise 2 to any of those exponents, then what you will get will be, well, it's 2 to the nth power raised to the x power times 2 to the q minus 1 raised to the y power, and if each of these separately is congruent to 1 modulo q, then their product is also congruent to 1 modulo q. So if I want a small exponent up there, what I should do is to choose the x and the y, positive or negative, so that this linear combination of those two numbers is the smallest it could possibly be. Well, you guys may remember that when you look for the minimal, at least the minimal positive number, that's a linear combination of something and something else, what you can get is the GCD of those two integers. that will be the smallest possible exponent that will work. So if you look at the GCD of n and q minus 1, oh, no, yeah, okay, I remember where I got stuck a second ago. There's 2 to this GCD, that will also be congruent to 1 modulo q. Okay, so any pair of equations like this, where it's the same base and a 1 on the right-hand side, but 2 different exponents, then you get another equation like that, but you can get these things to be quite small. The smallest that you can get, the smallest positive exponent you can get, will exactly be the GCD of those 2 integers. Well, all right, that's fine. I paused in the middle of the proof because I was like, wait a minute, I'm doing something wrong. I thought I was going to use the fact that q was a prime, and suddenly I saw the q minus 1s where I wanted to just see a q, and I thought something was going to get screwed up. What I forgot in the middle of my proof is that n is also prime. So when you look at the GCD of n and q minus 1, there's only 2 possibilities. This GCD is going to be a divisor of n. So either that GCD is equal to 1, or the GCD is equal to n. And in the one case, what you would be deciding is that 2 to the first power is congruent to 1 modulo q, and that doesn't sound so promising. 2 is never congruent to 1 modulo anything except for being modulo 1, so that's a contradiction. All right, you can never have q dividing 2 to the first minus 1 unless q itself is a 1. So the other possibility is that the GCD is just equal to n, and I didn't really have anything novel happening here. I mean, nothing novel happening here because this congruence is exactly the same as that congruence. But when you tell me that the GCD is equal to n, what that tells me is that, in particular, n is a divisor of both of those numbers, and that means that n divides q minus 1. Which is to say that q is congruent to 1 modulo n. And that's almost what I said I was going to prove. The difference is that I said q would be congruent to 1 modulo 2n, so 2n should divide q minus 1, not just n. Well, yeah, see, but I have something else up my sleeve here. If you take a prime divisor of such a number, I know that that prime is not 2. 2 does not divide a number that's 1 less than a power of 2, because this is odd. So this is an odd prime number, which means that this one here is even, and you're talking here about an odd divisor of it, because this n is also a prime. Oh, I should say n is not equal to 2. So you've got an odd divisor of q minus 1, and you also know that 2 divides q minus 1, and 2 and n are co-prime. So that means that if each one of them separately divides q minus 1, that means that 2n divides q minus 1, which is to say that q is congruent to 1 modulo 2n. So that completes the proof of this theorem. I can also take this word out, because now that I've shown that each one of the prime divisors of this thing are 1 more than a multiple of 2n, then any divisor of this number, of course, it's a product of its prime divisors, possibly taking powers of those prime divisors. You look at each of the prime divisors, if you raise it to any exponent, if q is congruent to 1, then q squared and q cubed and so on, those will just be congruent to powers of 1, modulo 2n, which is also just 1. And if I have a couple of different primes raised to different exponents, if everything is always congruent to 1 mod n, then their products are also congruent to 1 modulo 2n. So in the statement of this theorem, after you've proved that it's true for prime divisors, it's also true for all divisors. So with this theorem in hand, a search for divisors of your Mersenne numbers gets a little bit faster. You only need to be looking at the Mersenne numbers where the exponent is prime. And if you want to find a divisor of such a thing, only look for prime divisors that are 1 more than a multiple of 2n. And what you'll find if you want to continue this list is that there are lots of of Mersenne numbers are prime, but they do start to thin out. I will just tell you that the state of the art a few decades ago was such that I believe this was the biggest one that was known. For a while, this was the biggest prime number, and I think it was the University of Illinois. Some members of the computer science department checked that this was in fact prime, and they even had this statement, exactly this statement, that was the postmark on the outgoing mail from the University of Illinois for a short time. They were just so proud of this little discovery. Since then, we've got much bigger prime numbers of this type, but as I say, nobody knows whether there's infinitely many or not. All right, listen, this is all I'm going to say about the perfect numbers. It is true that these are the only even perfect numbers. These, I don't know, here, these are the only even perfect numbers. That is true. In fact, the proof is not very difficult. It's in your book somewhere in chapter 7. But the odd perfect numbers I pointed out to you, nobody seems to know whether they exist or not. I won't say more about these. I think this will be the end of chapter 7. And on Wednesday, I'd like to start on chapter 9, I believe it is, on primitive roots. I will not put that on the test, but I will have the test include the stuff that we've done on chapter 7. Our test also includes, since the last exam, we've also been talking about chapter 4 and chapter 6. And those would be the topics that I'd like to put on the exam. So the exam's going to be on Friday, and I will have office hours today and Wednesday. Those would be good times for you to ask me for questions you have about that material. Is there anything that you want to ask me today before we quit?
Is the exam, is it you give it to us on Friday, or is it going to be due on Friday?
That's a good question. I guess I didn't actually think that through, because I said I'd give you 24 hours. Let me, I'll tell you what, I will get the exam ready and I will email it and post it by sometime on Thursday, and then you'll have until the corresponding time on Friday to finish. How's that?
That sounds good.
Yeah, I'm glad you asked
We
me
also
that.
have a question on the chat. We still have class on Friday.
No, actually, I wasn't thinking that we would, because I thought you would be working on the exam on Friday. Do you want to meet on Friday?
I think we can work on the exam.
Yeah, I think your time will be better spent on the exam, although actually there's no reason we can't be. I had not planned to meet on Friday, let's put it that way. But now that you've asked the question, I guess I should think that through carefully. So the default answer will be no, we will not have class on Friday, but let me think about if there's a good way for us to use that term.
And so will the exam be due at like 2 p.m. class time or like end of day?
I mean, I guess I was thinking that since our class goes from 2 to 3, that I would rig things up so that you would have the exam by 3 p.m. on Thursday and you could turn it in by 3 p.m. on Friday.
Okay.
But I don't know. We're all making this up as we go along. If you guys have a preference, speak now, and now's a good time for you to let me know. Well, think about it. If something comes up, send me an email, and then I'll take that into account. But I guess I'll plan on getting you an exam by Thursday at 3, and then you'll have until Friday at 3 to finish it. Okay?
What sections exactly are going to be covered on the test?
Don't know. Let me look at the text. I'm pulling out my book here. So the last exam, we really were just flirting around with the first 3 chapters or so. I guess you guys had things like the Euclidean algorithm and Bézout's theorem on the first exam, right? But now starting right after that is when we launched into chapter 4, congruences. We talked for sure about the general, what they mean, how to solve linear congruences, the Chinese remainder theorem. We talked about solving polynomial congruences a little. So I would say pretty much all of chapter 4 except for 4.6. Chapter 5 is kind of right when the disasters happened, so we skipped over that and then jumped into chapter 6. We did discuss for sure sections 6.1 and 6.3. I didn't have a whole lot to say about 6.2. I mean, we mentioned it, but it's not really all that important for us in this class. And then now chapter 7, we've gone a lot into sections 7.1 and 7.2. And today was about 7.3 really. And this Möbius inversion, I mentioned it once when I talked about the Möbius function, but I didn't ever give you the theorem that's in there, the main theorem. So we'll skip that part. And partitions, not at all. Oh, and the cryptography, do you want questions about the RSA algorithm?
I don't think I do.
You don't, okay. I
did appreciate the lectures though. That was really insightful.
Well, it's fun. I mean, it is fun, and as you may guess, it's actually practical because people are doing encryption. But I don't want you guys to be wasting a lot of time trying to learn how to do high power, high exponent arithmetic, modular arithmetic, and that's what you would need to do in order to actually grind through some of the calculations. So if I ask you any questions about the encryption algorithm that we discussed, it would just be something that's really a question about like Euler's theorem or something. All right, think about it some more, and then on Wednesday, if you have more questions, you can clear them up with me. Okay? All righty, guys. Keep well, and I'll see you on Wednesday.
Thank you.
Bye-bye.